You know, I'm going to get a little philosophical on you, but I just realized, this class, the fact that it's been already 2 weeks since, it just shows how short our lives are, and how much we have to cram in, learning this stuff, doing it, retiring. So it just seems like I just got started in this, and I'm already, I've been at the university for 24 years, this university. All right, so I just shared that with you, so I will get on with this stuff now. For those of you who've had a classroom, I tend to, every once in a while, I'll do that. Isn't that right, Ms. Dorinya? She says yes. She shakes her head. So let's see where we are and where you are. So first of all, the homework, I pushed that back to Thursday. Everybody got that? Did I say that in the email? I did not say that in an email. Does anybody have their homework?
We just kind of found out about it last time.
Oh.
Someone printed it off early, and then someone printed it off later, and then you had changed the due date on it.
Yeah,
So.
I thought I had.
I think it's Wednesday though, right? It's
Yeah,
first.
Wednesday, not.
We have Monday,
Thursday.
Wednesday classes.
Yeah.
Not
What?
Thursday.
I
You
think
just
the,
said
the
Thursday.
due, I think the due
I put the
date's-
due date on Thursday. I'm still on Thursday.
Confusing everybody.
All right, okay, I'm confused. All right, the due date for the homework, let's go ahead and leave it Thursday. Since I put it on Thursday, I intended for it to be Wednesday, because that's when we
No,
actually.
I think it's on Wednesday, but you just said Thursday, so.
It says February 1st.
Hold on, let's.
Oh, I wrote
So,
it there.
so today I'm going to get reoriented. I've been, okay. You all know what's going on, but I don't. So let's go back to the home page. Where's Mr. Sanchez? Okay, because, okay, sorry. Well, let's go back to the home page. All right. February 1st is Thursday. Is that or is that Wednesday? No, February 1st is Wednesday.
Today's the 30th.
Right, tomorrow's the 31st. And Wednesday is the. So, this is correct then?
It was just you and said.
Okay, so, I thought I had sent you an email that said I was, Ms. Dorinya, did I send an email? And I said, in that email, I said that I was going to have you turn in your homework onto this, on the Dropbox instead of, I did say that?
Yeah.
Okay,
You said that, yeah.
all right.
I just thought you meant.
We're confused on the whole date.
Okay, now I understand why you're confused, but you had me thinking, I kept saying, I sent an email, and you kept saying, no. Okay, so I did, so you got the email. Homework is due on Wednesday, but I said Thursday, is what you said, okay. But it's due on Wednesday the 1st, and we'll go look at it here in just a second, and it is a Dropbox submission, all right? Which means you can either, do it like with Word or LaTeX or whatever, or you can just scan it and submit it that way. But make it a PDF, because I want to be able to annotate your homework electronically, and it's easiest for me to do that if it's a PDF. Okay, all right. So we're straight on that. So I'm going to summarize this course later today to summarize today's class, and just to make sure we're all on the same page. Now, so this is the home page. A couple of things here. So this was I had already put this up. Anybody download this thing, play with it a little bit? It's kind of interesting. This is that virtual. This is the DSMC virtual wind tunnel that we looked at on the first day, first day of class. Now, oh, there it is right there. I was about to say there's one other thing here. So here's my office schedule. Yeah, Mr. Gupta. Where's Mr. Gupta? Where is everybody? The two people who emailed me over the weekend aren't here in class today, so. So, office schedule. So right after class, from right after class until noon, is on Monday and Wednesday. Then on Tuesday from 11 to 12. Okay, and then I'm generally in the afternoons. I'll be there. Is there anyone in the class who can't make one of these two times? Because if you can't, then I'll maybe add in some time in the afternoon. Okay? So everybody's squared away on this. Now, Mr. Sanchez emailed me over the weekend to say that you can actually access this text that I copied the pages from. You can get to an e-version of this through Chinook, through the library. I didn't realize you could do that. And so this link here, you have to use your ID, your identity key to log in. But as you can see, it's right here, and so that's nice. It looks nicer than what I copied. Let's see if I can. So yeah, so it's a better quality than what I, the copies I put up. All right, so you can go right here. So the entire book is available to you online through that link that I have on the home page. Let's go back to where is the. This is Mr. Sanchez. I was just giving you credit, Mr. Sanchez, for discovering the e-version of the textbook. Okay. Where's Mr. Gupta?
I have no idea.
All right. So now let's go back to what's on the schedule. So homework 1 is due on Wednesday, and we're going to talk about it today. Homework 2, I will post today. It's already posted in the, if you go to the, it's in the homework assignments. And it'll be due a week from Wednesday. And it has to do with binary collisions of molecules. So we'll be talking about that probably on Monday. So the next thing I wanted to talk about before we got to did you do the quiz? Pretty straightforward, right? There was a typo on number 2 where was it obvious that it was a typo? Okay, good, because I wasn't intending to, those kinds of ridiculous looking kind of mistakes like that, those are typos. I mean, that's not what I'm trying to test you on is can you tell L from lambda? So can you do what? Which problem? Yeah, we're going to look at all of them in just a second. So the rule for the quiz is that if I say something write something that's ambiguous, or you can prove that I'm wrong in what I thought I was trying to say, then everybody gets credit for it. Okay. So you should look at those carefully so that everybody can get credit for as many problems as possible or questions as possible. The only thing I can't do, in order for it to be automatically graded, I kind of have to stick with true, false, and multiple choice types of questions. I like to have manipulation things, simple work through things on there, but we'll have to do those in class because they don't really fit well, or short answers. You can have short answers on the quizzes, but I want it to be automatically graded when you do it and not wait for me to have to go in and grade it. So we'll stick with that. All right, so let's go to the quiz and then we'll talk about the homework. There's a couple of things I want to say about the homework, give you a couple of hints, and if you haven't finished the homework yet. So, any questions so far? Most of you, there's only a couple of you that weren't in my class last fall, so you kind of know how this goes. Any questions, anything? Okay. And we'll finish up the class talking about the schedule for the next couple of weeks. So let's go back to assessments, quizzes. So I want to go to preview. Oh, in this class, your quiz score will just be an absolute score. In the fall, if you made above 70, you got 7 out of 10, I gave you credit for 100% credit. Now, I'll tell you what, let's make it 8 out of 10. If you get 8 out of 10, then that's as good as 100%. Okay? 7 was a little bit too easy. So this is a 6,000 level course, so 8 out of 10 scores as a 100%. And I'll write that. Does everybody agree that? It's not in the syllabus, so I want to make sure everybody agrees to that. Okay, so let's start this quiz. Okay. Mr. Torres. The Navier-Stokes equations provide a mathematical model of a gas as a continuum.
True.
For this model, the spatial coordinates and time are the independent variables, and the macroscopic properties, pressure, velocity, etc., are the dependent variables.
I believe I put true for that.
The spatial coordinates and time are independent variables, and the macroscopic properties are the dependent. You said true? Anybody say false? What is independent and dependent? What does that mean?
So depending on where you are in space and time, the pressure and the velocity will vary based on that.
Okay. Why don't do we have to write space coordinates separate from time coordinates? Is there a reason why we do that?
I think just convention.
Right, just because we're human and that's the way we think, right? We don't have to do that.
We have to discretize them both differently.
What do you mean differently? I mean, they have dimensions. The space ones have dimensions of length. Time has dimensions of time.
If you're integrating them in like some sort of code or something,
So
to come up with a grid for space, and then you need to come up with some sort of time integration for the time discretization.
yes, and there's no reason though that we couldn't write, for instance, a gradient operator, for instance, or an integral operator that is 4-dimensional. And in fact, if you take, how many of you took 5227, the aerospace math? Any of you take that? I don't know if you all talked about it, but one of the things I've done in the past in that class is to emphasize that point is to, you can write, there's no mathematical reason why you have to separate space from time. You basically have 4 dimensions. And you can write operators, 4-dimensional operators, and not have to do that. So it's just by convention, like Mr. Torres said, that we choose to do that. Do you have a question? Okay. So true? Okay. Mr. Gupta, we got started without you. All right. So now this, so this is the one here that obviously everybody's going to get this one. Did anybody miss this one, by the way? Do you know if you, well, you wouldn't know if you missed it or not, would you? Not initially. Because the way, when you take the exam or take the quiz, it gives you a score, correct? But it doesn't tell you which, if you missed one, does it tell you which one you missed?
It does tell you.
It tells you the one, it tells you the one you missed?
Yeah.
I don't want to tell you that. Is that the way it was last fall also? It always tell you? All right, got to change that. I thought from reading the way it's set up, I thought it was just telling you that you got like 9 out of 10. Okay, that's kind of ridiculous then. No wonder you all didn't struggle with those. I want you to struggle with these things. Well, that's going to stop. Okay, so it won't be telling you what the score is. Well, I want you to know what the final score is because I want you to know that you missed some, so you go back and do it again, but I don't want it to tell you the one you missed. Okay. Well, that'll be changed. So, the Knudsen number. Mr. Gupta, since I know you know the answer to this, is defined as with the lambda over L, right? Where lambda is the molecular mean free path. And it's the scroll thing doesn't work. It's the where the molecular mean free path is the average distance traveled by molecules between collisions. That should have been a lambda. This right here should be a lambda instead of an L, right? Okay, so everybody knows that's supposed to be lambda. So a rarefied flow is characterized by a relatively large value of the Knudsen number when the Navier-Stokes equations are no longer valid, somewhat greater than a Knudsen number of about 0.1.
True.
Right? This is basically what Bird said, but he also says that you have to be careful in how you define this Knudsen number, whether it's a global or a local number, because what's more important is not so much the global number, but what's happening locally. Now, when the Knudsen number gets relatively large, what's the first thing that breaks down? Why do we? What is it that signals that we can no longer use the Navier-Stokes equations? Is the boundary condition?
Transport terms, they vanish.
What about the? So the transport terms vanish?
When the Knudsen number is
Now
high.
I thought when they vanish, that corresponds to something else. What's that?
The Euler equation?
Yes.
Inverted Euler equation.
Right.
Yeah, right.
So that's when they vanish, and that corresponds to a Knudsen number of what?
Point
For the Euler equations?
infinite.
Zero, as it very
Yes, 0.
Yes.
Right. So a Knudsen number on the order of 0 would give you basically the Euler equations, and so you'd have no transport, right? And we talked, unless I'm dreaming, we did talk about this on the previous class. Okay. So you're saying that. So try again. You said that So a large Knudsen number means what about the transport? Well, my question is it the boundary condition that breaks down first, or is it the transport relations that break down that cause you to no longer be able to use the Navier-Stokes equations? Mr. last name?
Peters.
Mr. Peters.
Isn't it when the gradients become too steep in the strain rate? It's no longer like a linear relationship.
Yes, part of that. The second part of that is no longer, when you say no longer a linear relationship, linear in
But
what?
we have higher order terms that we
Okay.
can take care of.
Right. So that's what starts to happen. What about the boundary condition? Mr. Pointer? So once the no slip condition is no longer valid, then you can't use the Navier-Stokes equations, correct? Is that right?
Can you trick it
What do you mean?
by, applying some sort of slip condition with the Navier-Stokes equation?
You're exactly right. They are still applicable. It's just you have slip flow. So the progression is that you have the Navier-Stokes equations with the no slip condition, right? And Navier-Stokes, all that means, it has nothing to do with conservation of mass, and it has really nothing to do, well, I shouldn't say nothing to do, but when we say Navier-Stokes equations, what are we talking about? Momentum. And then when we talk about the constitutive relation, what is that? What are we talking about that is the thing about momentum that makes it the Navier-Stokes equations? Well, conservation is broader. So you start out, the big picture is conservation laws, mass, momentum, and energy. Then you have an ancillary auxiliary equation, I guess I should say, is the second law of thermodynamics, right? We'll get to that as to why that comes into play. But then you look at the conservation of momentum, and in order to go in from a if you look at it from an integral approach, you don't have to know any that detail, right? Remember when we did the conservation laws and we did well, I say remember, if you took 50-51, whether you took it from me or someone else, we did the conservation laws before we even said anything about the Navier-Stokes equations. We did conservation of mass, momentum, and energy, and did quite a bit of analysis, like a jet, land on a runway, all that kind of stuff, because we didn't have to pay any attention to the real details of what's happening point-wise. But then we introduced a divergence theorem, and we used the divergence theorem to convert the conservation of momentum to the Navier-Stokes, to conservation of momentum point-wise. And even at that point, we still had just a partial differential equation without any necessary details. But we had to go in and relate what? There's stress and rate of strain. And so we had to write, how does the velocity vary from point to point? And what we did is say at a given point, if we do a Taylor series expansion, we only need to keep the first order term in a Taylor series expansion to capture how the velocity varies from point to point, right? So that's the linear, when we talk about that linear relation, that's what we're talking about. Now, as you continue to break down, or as the Newton number continues to go up, the linearity it's not good enough, just like what you were saying, Mr. Peters, right?
Correct.
So I'm embarrassed to say, Katie, I know your first name, but what is your last name?
Lachine.
Glasheen. How many times have you told me that?
Couple.
Okay. So, Ms. Glasheen, have you heard of the Burnett equations?
Yeah, but I couldn't tell you what they are.
Okay. What happened, the Burnett equations are basically the next level up in complexity from the Navier-Stokes equations. So, the Burnett equations, and I think I mentioned in class, I'm going to stop saying this, okay? The Burnett equations take into account higher order terms, and so extend the continuum model further. But in the constitutive relation that we talked about earlier, there are additional terms. Now, there's a considerable amount of research in the 80s and 90s on the Burnett equations and methods to solve those or integrate those equations. There was some argument as to their validity because there were papers written about how that set of equations violates frame independence. Okay, and we're not going to get into that. And we're not even going to get into the Burnett equations. But that's next level up. Then you continue to go up. So your boundary condition is already broken down, right? And so you mentioned tricking the set of equations. You don't really trick the equations, but you do exactly what you said. You then set up a different boundary condition where there's slip. So that means that there's a jump where the no slip condition means that the fluid elements or fluid particles closest to the wall, or a wall, stick to that wall. They move, they have the same speed or same velocity as the wall. And, but the slip condition means that the fluid literally slips on the surface, okay? And so that you bring that boundary condition in along with, and you can continue the Navier-Stokes equations. That breaks down because of the transport, and then you move to the Burnett equations. Then after that, you essentially go to the full Boltzmann equation, which is what we will be doing in this class, and that's where you apply the Monte Carlo simulation. Now, we will not approach the solution of the Boltzmann or the simulation of the Boltzmann equation as you would do in CFD, for instance, with discretization, finite volume, finite difference type of discretization. Some people do that. It's very tough because there's a source term that we'll be looking at on the right-hand side of the Boltzmann equation that involves the collisions of molecules. It's very difficult to model, and So that's where the Monte Carlo simulation comes in, because we will then take a probabilistic approach to solving that deterministic equation. All right, there's a lot of talk in there, but basically back to the Newton number being large is associated with a rarefied flow. And what we're interested in, we'll see that when we get into what's called collisionless flow or free molecular flow, that means the same thing. It's really pretty straightforward, relatively easy with analytic formulas. It's the in-between, between the free molecular flow and the continuum, which is called the transition regime. And that has nothing to do with like boundary layer transition. This is transition from rarefied to, or from continuum to rarefied. That's where the Monte Carlo simulation comes into play. So this was true, right? It's supposed to be true. All right. Number 3. So let's assume that I wrote this correctly. So, Ms. Durenya, you had a question about this one. So, a local Newton number can be defined if the characteristic dimension L is written in terms of the local macroscopic gradients, for instance, for density.
Right.
Based on this, oh, okay. For an object moving at supersonic speed, creating a shock wave in a quiescent dilute gas, as the Mach number of the object increases, the flow in the interior of the shock wave appears to become less rarefied compared to the quiescent gas upstream of the shock wave. That's a lot of stuff. Do you understand what I was asking you? So Ms. Dren, you had a question about this. Let me just quickly come out here. Let's see, slides. I want to do this one. So what I'm saying is you have an object that's moving let's say it's, and there's a shock wave out here out front, okay? So if we zoom in on this and look at it, actually this goes to positive infinity and negative infinity. So if we looked at something like the density, what happens to the density through a shock wave? So let's just imagine this is the upstream location, this is the downstream in the shock wave. What happens to the density?
Be a sharp gradient.
Increasing or decreasing?
Increasing.
Flow is going in this direction. So this is m much greater than 1.
Increasing.
So the density will come in on this side, and you'll have some coming out the other side. So this would be rho 1, rho 2, something like that, right? Okay. What happens to the velocity?
Slow down.
Slows down, okay. So you'd have something going this way. So my question to you is, if you compared what's happening in the interior of the shock to what's happening upstream, oops. How do I, there's a tab. So I'm saying that this, the density over this, so is this true or false, Ms. Durenya, the
True,
statement?
but it should be a Knudsen number, not L, I think.
No, this is a characteristic dimension that basically is giving the, so it has units of length because of the dx here. So the units of the density will cancel. So basically this is giving a rate of, it's a dimensional rate of change, basically. It's not a rate. So how can we, if I'm dividing the actual density by the rate at which it changes, it's just a characteristic dimension, all right? It's a characteristic length. So if you take this and put this into the Newton number, so if you take the ratio of lambda over this, that then gives you a local Newton number, is what this is saying. So does everybody agree with that part? So my question to you then is, based on this, for an object moving at supersonic speed, creating a shock wave in a quiescent dilute gas, as the Mach number increases, what can you say about the gradient as the Mach number increases?
Became more steep.
That's correct. And so as the Mach number increases, you would expect, what does that say about the density on the downstream side? Right, it may look something like this, right? Okay. And so my question then was, the flow in the interior of the shock wave appears to become less rarefied.
Density is bigger, so it should be.
So you're saying it becomes more like a continuum? Less rarefied means it's more like a continuum, right?
If it should be more molecules there, like a shock wave.
Okay.
The density's higher, you should have more collisions, so it should be closer to a continuum.
Well, what happens to a shock wave as the Mach number increases? It actually gets thinner, right? The distance between the upstream and downstream is less. So what does that mean about the collisions? You have more or fewer?
Less, because it thins down, so the collision should be less.
Well, let's think about it. So if we're saying that the characteristic dimension is L over, well, not L over, is, for instance, density over d rho dx, where this is just taking the magnitude of it, if that's L, and we're saying that the Newton number, which is the number that will tell us whether it's getting more or less dense, is then equal to this lambda over L. So what are you saying about what is happening to L as the Mach number increases? Is it going up or down?
Down.
Right, it's getting smaller, right? So if it's getting smaller, what can you say about the Newton number? It's increasing. So it appears to be more rarefied inside of the shock. So it's kind of counterintuitive, isn't it? That although the density is actually increasing through the shock, and actually the density approaches a limit. Does anybody recall what that limit is in your high speed? Anybody taking high speed aerodynamics or gas dynamics? Mr. Matthew? Well, I'm not going to tell you. It involves the number 6. So, back to the question here. So, this actually says that the Newton number is
Avogadro's
increasing.
number?
What's that?
Avogadro's number for the limit of the density?
No, not yet. We are not talking about that yet. But we will be talking about Avogadro's number. So this is kind of counterintuitive. So what did you say on this? See, this is the reason why.
Can we say that our lambda is the same?
Lambda also does change, but not as abruptly as the density. So this is a little bit that the molecular mean free path, it starts to increase as you go through the shock wave, right? But if we look at this relative to what's happening upstream, then the Newton number will actually go up. I probably should have put an infinity on this like this in this instance. Yes.
Is that rail also like the free stream with when you're
This is
characteristic like
that in this case, yeah, yeah. So and that's one area of if you look at some of a lot of the research papers during the 90s or so, there was a lot of DSMC applied to shock structure. I actually have a paper we might look at that my former advisor and I wrote on looking at shock structure, although we were looking at dense gas dynamics, not rarefied gas dynamics. But you can actually solve one of the semi-analytical solutions to the Navier-Stokes equations is for solving the structure of a shock wave in one dimension. Okay, and so it's counterintuitive. So you're more likely to need to use, what this tells you is that the state of the gas becomes further and further from equilibrium as you go through the shock, as the shock wave increases. And so you cannot use the continuum approach. You have to use a molecular approach to account for the departure from equilibrium and also the increased Knudsen number. So this one, what did I say? Is this false or true? True based on what I just said. The flow in the interior of the shock wave appears to become less rarefied. It's false. All right. Generally speaking, the Navier-Stokes equations begin to fail because, we already talked about this, the gradient terms and the constitutive relations for the shear stresses and heat flux terms become invalid. Not before the continuum assumption becomes invalid. Agree? Yeah, we already did this one, so I'm going to. Oh, this is a good one. See, Mr.
Ryan?
Ryan, R-Y-A-N?
Yep.
Mr. Ryan, all molecules in a simple gas consist of a single chemical species with all molecules having identical structure.
True.
Yeah, it's true.
I thought that was a trick question because the book said we will make the assumption that they all have identical structures. And then your question didn't say we're assuming, it just said they're all identical. So I thought it was a trick question.
Oh, okay.
I still got it right, but
Okay.
made me
Good
question
point.
intention.
The title of this chapter is The Molecular Model. So everything about this chapter is an assumption, right? It's a model. So the point here, but you make a good point. The point here is that later on, we can talk about mixtures. Well, even in mixtures, you can still treat a mixture, but it's not a simple gas at that point because we're talking about identical chemical species and the molecules are all identical. And when we get into the discussion about the collisions, we'll start to talk about even more about the structure of the molecule, whether there's a force field or not, and so forth around the molecule. So this one was intended to be simply true. But the statement about the simple gas was a bit complex. All right. So I got to make sure I get the names. So Ryan and Peters. I was going to call you Parker. Maybe I was thinking about Spider-Man or something. So Parker. No, Peters. Yeah. Yeah. You just told me that, and I was thinking Parker. All right. The number of molecules, Mr. Sanchez. Have you already answered the question, Mr. Sanchez? The number of molecules per unit volume is the number density.
Yeah.
What are the units?
Molecules per meter cube.
A molecule is a unit?
Yes.
No.
No. Well, I guess that it would be per meter cube.
Yes, period. Yeah, you got it right. It's just per meter cube, right? It's a number. Number doesn't have units. The number density depends on the composition of the gas and is independent of the temperature and pressure.
False.
Really? What's false about it?
It does depend on the temperature, for sure. I'm not sure about the pressure.
Composition?
I think it doesn't depend on the composition, actually.
So you're saying that if I had nitrogen in a bottle, and I had a certain number density, if I then replaced all those molecules with oxygen molecules, I'd have the same number density?
Yeah, I think that was like Avogadro's.
You all really like Avogadro, don't you? Okay, Avogadro still doesn't have anything to do with this. Not yet.
But yeah, I don't think it depends on that.
So you're saying if I replaced all the, what did I say, nitrogen? If I replaced all the nitrogen molecules with oxygen molecules, you're saying the number density would stay the same?
Yeah.
Even though they don't have the same mass? You're right. Couldn't force him out of it. Okay, so this is false for the very reason that you said, right? And it does depend on the temperature and pressure. Yeah. A dilute gas is one for which, these are too easy. A dilute gas, Mr. Starnes, did you go visit your folks in Australia over the holiday? Okay. I don't think I actually looked at the FCQs to see if any students complained about me giving Mr. Starnes a hard time about being from Australia. His name, just his name, he sounds like he should be from Australia. Just kind of has a look about him too, the Irish, Australian, something like that. All right, sorry, Mr. Starnes.
Sorry.
A dilute gas is one for which the average spacing between molecules, delta, is much greater than the effective diameter of the molecules. So that means that the average spacing is much greater than the diameter, in which case the intermolecular collisions are overwhelmingly likely to be binary collisions.
True.
Okay. Anybody disagree? So what this means then, in a dilute gas, and we talked about, you're actually breathing a dilute gas, that means that from the model point of view, that the molecules spend most of their time in flight, not interacting with other molecules. And we can model that interaction, the only time they actually interact is when they collide. And the simplest model as we'll see is something called the billiard ball model, where literally you can model it like a billiard ball, to where the molecules only interact when they literally bounce off each other. Now, you can put in a force field model in which there is some force at a distance, but even that can still be, if that force drops off fast enough, you can still model that as almost like a billiard ball anyway, with some sphere of influence around it. So this is true. Classical thermodynamics is applicable to a system in thermodynamic equilibrium. See, who have I not? Mr. Matthew. Is that right? Classical thermodynamics. I don't know that he actually says anything about, this is my statement. I don't know that he says anything about classical thermodynamics. I'm asking you, you're graduate students in a 6,000 level course, so stuff in the book and out of the book should all be fair game. Classical thermodynamics is applicable to a system in thermodynamic equilibrium. Do you know of any other type of thermodynamics? There's classical thermodynamics. What's the other type of thermodynamics?
Applied?
No. Well, there's statistical thermodynamics, but non-equilibrium thermodynamics, which is still a very there's a lot of research still going on in non-equilibrium thermodynamics, okay? And virtually everything that we will do, and virtually anything you will do in pretty much any, unless you go into research in that area, you will depend on classical thermodynamics. So how do we deal with, oh, let me keep going. So that is why classical thermodynamics is often called equilibrium thermodynamics. It's true. Mr. Matthew, the continuum assumption requires that there be only small departures from equilibrium.
True.
The microscopic description, however, is not limited by any degree of non-equilibrium.
This is true just because I read the statement in the book, because I don't remember the reason.
But did you know what it meant when you read it? See, because we're going to be talking about velocity distribution functions. And we're going to be describing flows that are real flows. So how do we deal with, how do we write temperature and pressure and things like that? Those things are defined according to equilibrium thermodynamics, right? So what do we do if we're not in equilibrium? Does that mean we don't have temperature and pressure and those types of quantities? Mr. Fontanella?
As like in the continuum, it's like an average, right?
Okay.
Average, and then the microscopic level, you're taking discrete points of temperature, and the gradients are much larger. So
Okay. So let's back up a second. What does equilibrium mean? If a system is in equilibrium, Mr. Fontanella, what does that mean? You just said something about gradients. What does it mean about the gradients? There's not really any.
there's no gradient.
Okay. No gradient. So if there's no gradient, then we're in equilibrium. And we just said that we have to have equilibrium thermodynamics to do fluid mechanics, right? Or to do the type of fluid mechanics we're used to, right? So how do we... By the way, I'll post this scribble after class so that in case you go back and it won't always be scribble. This is kind of like some scribbling here, but sometimes I'll try to write neatly, but not right now. Let me just add I need to add some blank slides here. So just in case I need more. So you have a gas flow, Mr. Matthew, or Mr. Fontanella. And so you have 2 points, point 1 and point 2. And we just said that if a flow is in equilibrium, well, first of all, if the entire flow is in equilibrium, what kind of flow do we have?
Steady.
Not necessarily. Corresponds to a limit of the continuum equations that we've already talked about. The Euler equations. Okay, you're in equilibrium everywhere. So, if we write P equals a function of, say, specific volume and temperature, that means that we are applying equilibrium thermodynamics. Okay? So, but Mr. Fontanella just said that there are no gradients. So how can I have a P1 and a P2 that are different in a flow if there's no gradients? A gradient means that there's change over distance, right?
Local equilibrium.
What does that mean?
The gradients are small, so they're negligible.
The gradients are small, so they're negligible over...
Small distances.
Right. So basically what we're saying is that we can go in here and parcel up this flow into these elements, right? This is how we do in our fluid mechanics. We go in and we say we have these differential elements All of these have some, and each differential element is the smallest identifiable piece of that fluid. And within that smallest identifiable piece of the fluid, this little cube here I'm drawing, we can make the assumption that inside there are no gradients. But from point to point, if I compare two of these, there can be slight differences. So if we're going from this element to this element, I can have a slightly different value for pressure. But within it, so I make the assumption that I have basically a closed system here, and that within that closed system it's in equilibrium. So this is what we call local thermodynamic equilibrium. And that's the basis of the continuum approach that we can apply it, is that we have local thermodynamic equilibrium. Now with Monte Carlo, with rarefied flow though, or I should say a molecular description, we don't have to make that assumption. So going back to that shock wave, so one of the reasons, the Navier-Stokes equations technically are only applicable up to a Mach number somewhat less than about 1.5. I think Bird says about 2, but really it's somewhat smaller than 1.5. That's because at low Mach number, you come in here, and I'm going to exaggerate this, and oops, trying to draw this. You have a small gradient, so relatively small gradient. So if you go in here and look at the fluid particles, they pretty much, you get a chance to, the gradients are small enough that they can be relatively negligible. But as you increase your Mach number, not only does the shock get more narrow, the gradients get much more steep. And in that case, the continuum breaks down. This is another reason why the continuum breaks down that we were talking about, is because you can no longer assume that the gradients within a fluid element are zero or negligible, okay? But the thing that makes the molecular approach nice is that we don't have to make that assumption. So back to, let's see, this one. So we have here that the microscopic description is, however, not limited by any degree of non-equilibrium. That's true. Let's finish this out so we can talk about the homework before. I've been dragging this out too long. The collision cross-section of a molecule with a force field is a function of the relative speed of the colliding molecules. Mr. Matthew?
Shouldn't the question be the collision volume of a molecule?
No. I meant to say collision cross-section. So what is the collision cross-section? Well, first of all, what do you mean by collision volume? Let me ask you that, to make sure I'm not saying no to something you may be right about. So there's a diagram, and I think it's in the slides also, but if you look at a molecule, and you imagine that it's moving through a field of other molecules, and for purposes of illustration, those molecules are fixed, okay? We know they're all moving, but we can look at a relative velocity. And so if it's a billiard ball, then any molecule, and it's a simple gas, so they're all identical, then any molecule whose center comes within d, which is the diameter of this molecule, for instance, if the center comes within d of that molecule, they're going to collide. If the centers, if you measure the distance between the centers, and that distance here is less than d, that means and they're headed toward it, that means those molecules will collide. Closest approach, if closest approach is less than d, okay? So now let's imagine that a molecule has a force field around it. So maybe larger than the physical, say the electron cloud or whatever. So let's say that it actually, here's the molecule here, but it has a force field that reaches out some distance, again, d, where d in this case is not the diameter of the molecule, but the diameter of the force field. So in that case, the same thing applies. That any molecule in which now this D right here is the diameter of the force field, then any molecule whose center comes within, the closest approach comes within D, there's a collision. So basically this is, you can think of this as a collision cross-section. It's like a target, okay? So anytime the center of a molecule, another molecule is within the collision cross-section of a given molecule, they're going to collide. So that's what we're talking about when I say collision cross-section. So my question though is, or the statement is it true or false that that collision cross-section depends on the speed? Right? That's what I'm asking. Yeah, the relative speed. Does that make sense? Should it matter how fast the molecules are approaching each other, how big that target is?
Did Bert come up with the variable hard sphere model that takes into account the energy of the molecules?
Yes. So the answer is yes, that it does. I mean, it's not immediately intuitive that it should, but the collision cross-section does, as we'll see, and just what you're talking about, the variable hard sphere model and the variable soft sphere model and so forth, that collision cross-section does depend on the relative speed. So think about it. What do we know, and this is relative to your homework, what do we know about the viscosity of a liquid? Let's go back to Mr. Starnes. I don't think did you finish answering the question I asked you?
Pretty easy question, so I just said the answer and we moved on.
Okay. So this is not so easy. So from 50-51, viscosity of a fluid. As the temperature increases, what happens to the viscosity of a fluid? I mean, of a liquid.
I always get velocity mixed around in my head, so it gets
No,
thicker
I said viscosity.
Yes, viscosity.
Okay.
The fluid gets thicker as the viscosity goes up or down. I always get that mixed around in my head.
Okay.
So I'm going to just say thicker or...
No, I didn't say, no, I said viscosity. So thicker has to do with density, right?
Well, yeah, but
So are you thinking about stickiness? Is viscosity related to stickiness?
yes, kind of, not
Nope.
really. Okay, what was the question? Let's just move on. I'll
So
figure it out.
let's talk about a gas, because that's what we're talking about. Oh, by the way, everybody stand up. You got to do this twice, class. So while you're standing, Mr. Starnes is going to. So a gas. What do you know about the viscosity of a gas? What happens with respect to temperature?
Does it, it decreases, right? They're inversely related?
The viscosity decreases with temperature in a gas?
No, they're proportionally related. It increases.
The viscosity increases with temperature.
Yes. Final answer.
Okay. Does that make sense to you all? Is that what you know? Is that the same for a liquid?
I believe it's different for a liquid.
What's different?
Isn't it the opposite for the liquid?
What does that mean?
It's inversely related for the liquid. As temperature increases, the viscosity decreases for the liquid.
That's correct. Okay. So let's think about, you can go and sit down if you like. So if you think about it, would it make...
Enjoying it.
Oh, you can stand up, please. You can stand up as long as you want, because the camera, I'm on camera, you're not. So if you all want to stand and walk around to the back of the room, feel free to do it. Seriously. Now, let's think about it. All we have are molecules now. Everything that we're going to derive in this class is coming from molecules colliding, period. Okay? That's the beauty of the molecular model, is you don't have to have we're not going in and discretizing, flux difference splitting and all this kind of stuff. We're literally just looking at the physics of molecules bouncing off each other. And we're going to simplify that down to just two at a time. So if we're modeling this as molecules just bouncing off each other, oh, that's telling me my office hour starts at 11:15, I think. So what do you think happens to the collision cross? So the viscosity is related to the collision cross section. Based on, let's continue this thread of thought. If the viscosity is increasing as the temperature is increasing, what do we know about the speed of molecules as the temperature increases?
Increases.
They're going faster, right? And so what does that tell you about the collision cross section then as the temperature increases? Because the molecules are moving faster, we know the viscosity increases, so that tells you that the molecules are getting, getting in each other's way, I guess, if you will, more with increasing speed. And so there's a relation then between the temperature, the speed, the collision cross-section, and the viscosity, okay? So viscosity, I mentioned, I was giving you a hard time because you said thicker, okay? Doesn't have anything to do with thickness, right? And it doesn't have anything to do with stickiness, because stickiness is really associated with friction. Viscosity is associated with what?
The rate of transfer of energy.
Is it energy?
I guess.
It's momentum. It's momentum transfer, right? That's the transfer related to viscosity. So, so viscosity does not have anything to do with, it's not stickiness and it's not thickness. It's related to the momentum transfer, right? So this is a function of the relative speed of colliding molecules. True. Let's get to this last one. The microscopic state of a gas is in a specified volume is defined by the position and velocity of every molecule in that volume. This combination of position and velocity is called phase space. Mr. Peters? Phase space. It has nothing to do with Star Trek.
I don't remember.
It's true. The combination of position and velocity, so 6 dimensions there, is phase space. In general, 6 dimensions. The one-dimensional flow of a gas of structureless billiard ball molecules is defined microscopically by 3 dimensions in phase space because each molecule has only one velocity component and one space component. Bird specifically was talking about axisymmetric, no, he's talking about one-dimensional flow. And he says that, what did he say? I was taking this from what he said. He says, and I wanted you to think about what he was saying. I'll put these on. He says, a one-dimensional steady flow of such a gas becomes a 3-dimensional problem in phase space. He says, I'm going to go back a little bit further. In the simplest case of a monatomic gas with no internal degrees of freedom, what does that mean, no internal degrees of freedom? This is a little on the first page of the...
Talking about the vibration of the molecule.
That's right. Vibrational modes, rotational, and so forth. The additional dimensions of this phase space are the 3 velocity components of the molecules. A one-dimensional steady flow of such a gas becomes a 3-dimensional problem in phase space. So what are the independent variables here that give you 3 dimensions in phase space? I already said in general, you would have 6, right? You have 3 velocity components, you have 3 position components. As a function of time, as functions of time. He's saying here, if you had a one-dimensional flow, you have 3 dimensions in phase space. What are the 3 dimensions I'm asking you? Well, one is position. That's 1 dimension. So how do you get 2 dimensions in the velocity space? So we're going to start talking about velocity space, where we look at, this is physical space, distance. But velocity space, you have units of speed on each axis, yes.
Is one rotation? Or is it just,
Well, he talks about the reason why the velocity distribution reduces to an axisymmetric distribution, right? For a one-dimensional flow, it means that you have a dimension in the velocity space, you have a rotationally symmetric velocity space. Okay, so when you read that, hopefully that's what you were thinking in your mind. You were thinking when he said that, you were visualizing that. But how many of you visualized that when you read it? That's the reason why I'm asking you about it, because I suspect that when you read that, you might not have thought about it. But pay attention to that, because I'll probably, on the first exam, have you draw this or sketch it and show what it means to show you understand it. All right, so this one's true. Oh, wait. Oh, I said it has only one velocity component and one space component. It's false. That's false. It has one space component, but how many velocity components? 2.
Sorry, can you explain? So we have that axisymmetric velocity and then
The velocity distribution is axisymmetric, not the velocity. The velocity is one-dimensional here. It's the speed, just basically when you talk about velocity in one space, but the molecules still have, they're still carrying these other components of velocity with them. See, that's the thing about, even when you do a DSMC simulation of a one-dimensional flow, you generally the molecules still have 3 velocity components. Now, what he's saying is that 2 of these components are basically redundant. But in general, a one-dimensional flow of a gas being modeled with a molecular model, you still have to, each molecule still has 3 velocity components. All right, so let's look at so that one was false because what I just said. Let me make sure did I make that false? Where's the answer?
But if you have 3 velocity components and 1 position, then how are you getting
Because 2 of the velocity components are identical.
2 are identical?
Right. That's where you get the axis symmetry.
Okay.
So if you went into, so we're going to talk about this on Thursday. We're going to actually go into velocity space and draw what I just said, because you're probably not used to thinking of velocity space. And so that's you got to get your mind wrapped around that. And so once you get your mind wrapped around velocity space, or physical space, we all are familiar with that. But we got to put these together. So the full, what's called the Liouville equation, we're going to focus on the Boltzmann equation, which is a simplification of the Liouville equation. The Liouville equation you would have to write, for this room, for instance, the position and velocity of every single molecule in this room would go into the Liouville equation. That's impossible. We couldn't possibly do that. So you start reducing that down till you get to the Boltzmann equation. And the Boltzmann equation we're going to find is going to allow us then to write, if we can write an expression for the collision between 2 molecules, then we can describe the motion in this space for all the other molecules over the space that are described by the Boltzmann equation. That's going to be the focus of what we're going to be talking about for the next week or so. So let me just quickly go to the homework and give you a couple of hints in case you haven't done it. Anybody finished the homework yet? Or think you finished it? So on this first problem, I don't really have anything to say about the first problem. Where the mute? No, I do have something to say. Oh, this is the first problem. Now, I don't have anything to say about that problem, but I do have something to say about problem 2. One of the keys to that problem is, what did I do with, there's 2 things I want to say. One is that the viscosity goes like temperature to the 1/2 power. Okay, make that assumption. And the other thing is to write the the mean free path like so. I'm going to show you here. Lambda is equal to, did I write that down here? I guess I didn't. Actually, this goes in problem 1 also. 1 over square root of 2 pi, because I don't think Bird actually writes this anywhere in the first chapter.
It's in the end.
What's that?
It's in the very end. That's where that's from the variable hard sphere model, right?
Right. Does he write it like this, or does he write it? I think he writes it in terms of ratio of the speeds. I don't think he actually writes it in terms of an average. Well, this is an average diameter, but I may be wrong.
I think at the very end.
Okay, good. Because if he writes it this way, this is the form you want to use for problems 1 and 2. All right. And the last thing I want to say is that in general, x plus y plus z, the average of a sum is equal to the sum of the averages. That's for the problem 3. That's a hint. And I don't think there's any hints for problem 4. I think I wrote a hint on the paper itself. And you can still work it a long way, but this the hint I have at the bottom will shorten the problem. All right, so this is due by 10 a.m. on Wednesday, not Thursday. Okay, so I'm on track now. I think for this class, I know it's not meeting on Tuesday and Thursday like it has forever, and so I'm very confused, as you could tell. Any other questions at this point? So I'll summarize later this evening what we talked about today to make sure that I'm on the same page with you in terms of where we are in this class. All right? So I'll see you on Wednesday.
No, I have to go do some stuff.